Okay. And can you guys see the Shield bot on the presenter screen? Okay, excellent. All right, well, welcome back everyone to the Shield bot with Arduino workshop. Today we are going to start by a little bit of review and covering a few items that I on Monday. After that, we'll experiment with our speakers a little more. I know you did that for homework, at least to get started, and there's a few extra things to try out. Next up will be robot navigation, and we'll also talk about some programming techniques, those being functions and arrays. And then after that, we'll move on to navigation by bumping into things using whisker contact switches. Last but not least, we'll have some questions and answers and talk about the homework. As always, please feel free to jump in and say, hey, Andy, I've got a question. Just unmute yourself. We don't need to be overly formal here. And if my answer turns out to be long, I might say, let's wait till after the workshop is done, but otherwise I'll do my best to answer the questions as we go. All right, so your homework was, this is the email I sent out for the homework. So it includes a recording to the YouTube recording of the previous session and slides. And then the homework was actually to download this robotics with the BOE ShieldBot example code, and then make sure that you can access that. So for example, if I show this in my file browser, okay, we want to go ahead and unzip it. All right, so we're always going to want to open the folder that we unzipped. Some computers will allow you to navigate inside the zip, but most of, I know at least the Arduino IDE editor won't want to try to actually open a project from there. So as an example, if we start the Arduino IDE, it should be appearing anytime now. Here it is. Okay. If we start the Arduino IDE and go to open up that, we can do file open. And so I unzipped it straight into downloads. And if you sort downloads by date modified, it's going to filter to the top. So we can go in there and, for example, look up some code from chapter 3 on the start reset indicator, which hopefully you did as your homework. And so we want to make sure that I want to make sure that everybody can open it with their particular IDE. So I'm going to show you how that works. Now, in the IDE, it opens in another window. And then we'll also look at the Arduino web editor and code bender in terms of opening the files. So here we are with the file, and we'll go ahead and run it. Hopefully I'm still connected. Compiling sketch, so it shows me the status down here. And an error occurred, which probably means that I don't have the right port selected. There's the Arduino Uno. Then try again. Was that audible? I'll go ahead and redo it, press the reset button.
There you go.
Okay.
Definitely.
Yeah, so so we want to, I want you all to run this test and make sure that you can open a project and run it and have it run. And ideally, that's going to be from chapter 3 and the name of the sketch is Start Reset Indicator. All right, so moving along, we'll do that with the Arduino web editor because it's a little different here. So there's an import button. So we're importing from our computer to the web editor. And so let's see here. Go to downloads, code, chapter 3. Just for fun, we'll go to chapter 4. This, you guys will get to try this later. Downloads, chapter 4. Play notes in array. And so that's how to open it with the Arduino editor from your local file. There, you all have noticed a little note about zipping all your files together and then uploading them in bulk. And so if we run this, little extra that you can do with your speaker. And then in Code Bender, hamburger menu on the upper right, open. I'm going to just select the same file. And we can get to hear the solfege notes again. That's what the do, re, mi notes are called, which was news to me because I never took any music classes. The device is unresponsive. Is that possibly because I have the wrong port? Or will the Arduino IDE not let go of it? Or pardon me, the Arduino web editor. There we go. Upload successful. Okay, so that is opening the downloaded example code in all 3 editors that you might be using. Very important point. Let's see, we have the, I should paste that in just in case anybody has not already downloaded it. So here is that. That's the pre-written code zipped. Make sure to unzip it before, and then go browse to the folder when you're opening stuff. All right, are there any questions so far? Excellent. Hey, let's go ahead and move on. Quick review of some things that I didn't quite make it to on Monday. This is the breadboard on your BOE Shield. And the breadboard is actually just this white plastic thing in the middle here. There are also some additional sockets that are attached to, so the black rows columns of sockets around the breadboard are also important for prototyping. Up top, we have voltage supply, basically 3 different voltage values where Vin is just your battery pack voltage. Down below, we have ground. That's the negative terminal of the battery pack. And then Vin is the positive terminal of the battery packs. It's usually around 7.5 volts. But that varies with batteries and how much life they have left. There's some analog inputs. And then along the side here, these are digital IO pins. So you can plug into here. And when you have your script or your sketch, pardon me, say to interact with one of the Arduino pins or sockets, that can be jumpered from here to the breadboard. Now, how do we connect things together on a breadboard? Many of you know, some of you might not. So just a quick intro to that. The breadboard is separated into rows of 5 sockets. So all these rows of 5 sockets can be used to connect up to 5 wires together. If you pick a different row, you can connect up to 5 other wires to each other, but they won't be connected to this row of 5 or this row of 5. So a row of 5 is for connecting 2 or more wires. So if you'd like to check yourself on that, take a look at this and let's see why the blue and yellow wires are connected on the left. Well, here they're on the same row of 5. Here they're on the same row of 5. Here they're not on the same row of 5, but we have this little nice jumper wire that's connecting 2 different rows of 5. So it actually establishes electrical continuity across all 10 sockets here. Again, unmute yourself for questions if anything is not clear. Here we have 2 wires going into 2 different rows of 5. They're adjacent to each other, but it's not the same row of 5. So these 2 wires are not connected. Likewise, with these 2 wires, there is not a jumper wire connecting these 2 rows of 5. So again, because they're in different rows of 5, they are not connected. Some other things you'll be working with soon are resistors. It has a very tiny peanut-shaped case with 4 stripes on it. There are 3 stripes that tell you what the resistor's value is. And a resistor resists the flow of electricity. So this resistor is yellow, violet, brown. So if we go and look at the color codes for that, we'll see that yellow is 4 and violet is 7. Those are the first 2 digits. The other thing that resistor color codes have is the number of zeros to add. That's the 3rd stripe. Brown is 1. So we'll add 1 0 to 47. That's how we get 470. The gold or silver stripe will tell you how precise the resistor is. In other words, how close can you expect it to be to 470? All the resistors in your kit will have gold stripes here. So that's plus or minus 5%, or so that would be 5% of 470. So basically pretty close to 470 ohms. And that's a fairly small value. We'll even be working with 10,000 ohm resistors shortly. This is a light emitting diode. It's also in your kit, and we skipped the part in the book since there's 4.5 hours to do all this. I didn't walk everybody through it, but there are lessons on, hey, this is a light emitting diode. When you put a light emitting diode, connect it in series with a resistor, and then connect all that to the positive and negative terminals of some kind of voltage supply, like a battery, you will see light come from the light emitting diode as current flows from the battery's negative, or well, current is considered to flow. If you think about electron flow, it's considered to flow from the negative terminal to the positive terminal. In schematics, you'll see that as the reverse. And speaking of schematics, the book always introduces the schematic symbol along with the part drawing. And although we supply solved schematics for all the schematic drawings, as in wiring diagrams, it's hoped that even if the goal of the class isn't necessarily electronics, if it's more computer science oriented, that still students will start seeing, well, gee, there's this schematic drawing that's by the wiring diagram, and there's rules of correspondence that you kind of pick up along the way if you don't necessarily, well, it's explicitly stated in, I think, chapter 3. Or no, it's either chapter 2 or 3. I'll have to go back to that. Let's see, 49 to 52, whatever that is. I'm sorry, I'm not remembering off the top of my head. So anyway, what we do in the chapter where we centered the servos is we started off with connecting these indicator lights, because these indicator lights are actually going to be able to show what the servo signal looks like to a human, which is a very rapid flicker that actually just appears to be dimly lit because the signal is so rapid And so here's an example sketch that turns the light on and then off. So in Arduino, it's important to set the pin mode to output if you're going to have statements later that turn the light on or off. A statement that turns the light on is digital write 12, high. And this light circuit is connected to pin 12 here and then ground up here. And that causes the light to come on. A delay causes it to stay on. And then digital write 12 low turns it off because it actually connects inside the Arduino. Digital write 12 high causes the Arduino to switch its 12th socket here to the 5-volt supply. Meanwhile, the other end is at ground. So that establishes the electrical pressure across the circuit that drives the electrons through it. Now, when it says digital write 12 low, it actually internally connects pin 12 or socket 12 to ground. Ground's also on the other end of the circuit. No electrical pressure, no current, no light. Then it introduces timing diagrams, and it actually introduces timing diagrams in more steps than I'm showing here in the slide. This is just the first step of the timing diagram where it shows, hey, if you were turning the light on for half a second and then off for half a second repeatedly, this is what it would look like if you graphed it, and that's called a timing diagram. And so 1,000 milliseconds or 1 second, 1,000 thousandths of a second, half of it's high, half of it's low, and this is what happens to the light as a result of that timing diagram. And what it does is it steps you toward the high speed signal that will rapidly turn the light on and off so fast you can't see it. But we start out with a servo signal that's in slow motion so that you can see it. And then the sketches continue to go faster and faster until we get up to the speed that you need to control these guys, which we talked about already. All right, so we should all have, with the exception of this circuit, well, the speaker will be on there, but not the rest of the stuff. We should all have this built. And one thing that you hopefully did and got to hear your speaker in response to this sketch right here is, well, you went ahead and plugged it in, and it's important to make sure you know where the pins of the piezo speaker are going, because otherwise, if you plug in wires above or below that row, there won't be a circuit for the speaker to actually make sound with in response to this sketch. So if you ran this sketch and your speaker didn't make sound, what you want to do is check and make sure that the speaker pins are in a particular pair of rows of 5. And then that the other connections that the book guided you through are also in that same pair of rows of 5. So if I lift up the speaker a little bit and peek underneath, I'm going to see a pin right there and right there, so that this row of 5 goes to one of the speaker's terminals to ground. The other speaker's terminal connects to digital pin 4. So once that is set up, what this does is in the setup, which only runs once, it has serial begin 9600, which in the homework before the class, you probably use that numerous times in order to see messages from the Arduino in the terminal. And so it prints beep, and then it uses the tone function call to say that the speaker is connected to pin 4. We want the tone to be a 3000 repeats per second. I'll get to that in just a minute. Tone, or a 3000 hertz or a 3 kilohertz tone. And the book also talks about all these things. And then the amount of time we want that tone to play is 1 second, 1000 milliseconds. Now, in order to that's a set it and forget it function call. So we also add a delay so that nothing happens while the tone is playing. And then it moves on to the loop, which just automatically repeats infinitely. And it says waiting for reset over and over again once every second. How are we with that? Everybody okay? Getting thumbs up. Okay, now remember, unmute yourself and say, hey, Andy, there's something I'm not clear on here. All right, inside the speaker, there's something called a piezoelectric element. I encourage you folks to use this slide. This is not part of the book. This came from something I was writing later, but it took a lot of work, so I want everybody to use it. So a piezoelectric element has a particular shape. It's kind of flat when both sides of the piezoelectric sandwich that are separated by something called a dielectric, both these pieces of the piezoelectric element have just a flat shape when both ends are connected to ground. Now, if you connect it to 3 volts, the piezoelectric element actually bends in response to the voltage. Okay, great. So what happens if you rapidly send high and low signals, like maybe 3,000 repeats per second of high and low, which is called a hertz, 3,000 hertz, or 3 kilohertz is another way to say 3,000 repetitions per second. When P4 sends that to the piezo speaker, what it does is it causes the speaker to deform, rebound with each repeat of that high-low. And that's what causes it to vibrate at a rate that is an audible tone. All right, now, whatever you do, don't take that piezo speaker off. We're going to leave that on the whole time, even though some of the pictures and drawings might not be showing the piezo speaker. Leave it on there. We consider it to be a reset indicator. And incidentally, going back to, I think that was in the Arduino IDE. Okay, so here we are in the Arduino IDE with that sketch I talked about earlier. Now, when I load that sketch in, okay, so you can hear it. I'll even start the, okay, so it says beep and then waiting for reset. Now, when I press the reset button, it beeps again and then goes into that loop of waiting for reset. The reason this is important is because if your students are using the ShieldBot to navigate a maze or essentially do whatever they're doing with it, and it stops in the middle of what it's doing, and you hear that beep, what that is probably indicating is that either you have dead batteries, or maybe it made an abrupt motion and one of the batteries got loose and fell partially out of the battery pack. So that's why at the start of every sketch that involves robot navigation, we put a beep. Now, another reason we have a beep at the beginning of the sketch is because when, see how well you can see it. When I start the sketch, okay, I'm going to press and release the reset button now. Do you see how that wheel turned? So another thing that the beep does is it gives the students time between when they start the sketch and when it really starts navigating so they can set the robot down. Now, another way to deal with that, that little twitch in the left wheel is to move the servo connections to the other 2 ports, but that involves a slight adjustment to every example sketch as well. I've been on the email with a couple of you about that. And so if you have any further questions, give me a shout out now, or we can talk about that afterwards. I'll try to remember to mention in an early navigation sketch how if you move your servo cables to the other 2 ports on the board, what to change in the sketch. It's very simple. All right. So now here we are with the robot. I'd like you to check a couple things. Actually, first of all, I'd like you to check and make sure that the breadboard is in the neighborhood of the front wheels. These are the front wheels here. And this is the tail ball underneath. So if your ShieldBot is if your shield is on backwards and the breadboard's back here by the tail ball, go ahead and loosen the 4 screws on the corners, take the board off, give it a 180-degree turn, put it back on so it looks like that. But if you have it like this, great job. Next
Andy,
up.
I have a question for you
Okay.
that might fit in here. Are there any rules to when you have your power plugged in and your USB cable plugged in? Are there certain things you should do first or second, or does it not matter when you plug and unplug cables?
No combination of plugging and unplugging those cables can hurt the robot or your computer. However, well, actually, all right, I'll give you one rule, and that is if you're like this with the battery power disconnected and the USB power connected, try to keep the 3-position switch right here in either position 0 or 1. We don't want to have it in position 2 if you have a sketch that's running the servos, because the servos, we don't want to try to ask your computer's USB port for enough power to run these servo motors. So I'd say that's probably the most important thing to keep in mind. Aside from that, in terms of connecting or disconnecting, there's no hard, fast rule for the order that you have to do it. So again, basically, if your robot's going to move with the 3-position switch in position 2, you always want to have the barrel jack or the barrel plug, which is this, connected to the barrel jack here.
So Andy, that means we're drawing power from the computer and the battery pack together all the time.
Well,
and why is that?
When you're disconnected from you, okay, so your robot will need to roam around, or one of the goals is going to be to have your robot run some kind of obstacle course. And so at that point, you'll be disconnecting the USB cable, and it'll be running strictly off of batteries. Whenever your 3-position switch is in 0 or 1, see if I have a visual aid nearby. Okay, so here's the 3-position switch that's on the board. So when it's in 0, that means the power to most of the system is off. When it's in 1, it means the power to everything but the servo motors is on. And when it's in 2, it means the power to everything is on. And that's the point when you always want to have the battery connected, regardless of whether the battery pack connected, regardless of whether the USB cable is or is not connected. You want it to, you want to have it in position 2 so that the servos pull their power from the battery. Did I answer your question, or is there more to it? Or did I miss?
Yeah. There is one more little piece to it.
Okay.
When we calibrated our servos the other day on Monday, and we loaded a sketch. So the sketch went into the Arduino board, and it allowed us to do that operation.
Yes.
How much room does the Arduino board have? Does it just hold that sketch and then that sketch disappears, or does it hold several sketches?
It holds a single sketch. There may be advanced uses where it loads sketches from somewhere else, but the stock Arduino, each time you load a sketch in, the other sketch that was there before goes away. But it does hold a sketch. So for example, do I need to is this okay? Can you guys see this robot? Okay, if I hit the reset button, that basically interrupts the Arduino from running and it restarts from the beginning. And that's when we get our speaker beep right now. Basically, any sketch that you load is going to be in there until you load another sketch. So regardless of whether you've completely disconnected power or not, it still saves the sketch. And if you think about that from the Got Brains, initial product, what's inside a product, how this provides a window to that. All the products like the microwave oven and the digital alarm clock and things like that, they have to keep the firmware sketch that was loaded into them as a product, so that every time you turn it off and back on, it still has its program that it runs. And so that's just a kind of a standard way that microcontrollers work, including the Arduino. All right, cool. So let's see, where are we going next? I think we were talking about direction. Okay, so forward, you want to imagine that you're sitting on this breadboard here. Maybe your feet are hanging off the front of the robot. So forward is going this direction. Left turn and right turn are likewise, if you orient to forward, then backward, left, and right all come from it. Now, some students and maybe some of you will be surprised to find out that when the wheels are turning the same direction, this thing will just spin in place. In order to have the ShieldBot go either forward or backward, well, let's think about it. If we look at the right side of the ShieldBot, what direction do the wheels have to be turning? Looks like clockwise to me. This right wheel has to be turning clockwise for forward translation. Now, if we look at the left side, so forward would be this way, and the wheel has to turn like that. Now, if we look at the right side, forward is this way, or I'm sorry, if we look at the left side, the other side, the one by the servo ports, forward is this direction. And to make this wheel push the ShieldBot forward, it has to be turning counterclockwise. So if you want your ShieldBot to go straight, either forward or backward, it needs to have its wheels turning at roughly the same speed, but in the opposite direction. So an example of that is here in servo runtimes. So now it's you guys' turn, pop quiz. We want to open this with our Arduino programming tool of choice. So look inside the chapter 4. So go to your programming tool, hit the open or import button, and then navigate to the folder you unzipped. Look inside chapter 4, and you'll see servo runtimes. I'd better do that too. See, I'll do it with the Arduino editor because that takes the longest. Import. Okay, I got to go up by 1. Downloads, ShieldBot code, chapter 4, servo runtimes. Might help to sort by name here. Oh, did I get, no, simple function call, where's servo runtimes? Okay, I gave you guys bad instructions. Bear with me a second. Let's go back up a level. Servo runtimes might be in chapter 3. Okay, what's going on here? All right, let's go ahead and open forward 3 seconds. So go into chapter 4 and open forward 3 seconds. Sorry about that. I think servo runtimes may even be back in chapter 2.
Yeah, it's in chapter 2.
Okay. Okay, so I needed to go forward one more slide. What I meant to say about servo runtimes is that it would make this the robot turn in place. And you're welcome to try it, but what we want to do is on the next slide, which is forward 3 seconds. So again, chapter 4 subfolder, forward 3 seconds sketch. Set your 3-position switch in position 1. Make sure your battery pack and USB are plugged in. You may need to hold the robot up, otherwise it might try to jump off your table. After you've loaded the code, you can hit the reset button to make it restart. Forward 3 seconds. Load the sketch. Okay.
How long should it take for this to open or upload?
I'm not exactly sure. Are you using the Arduino web editor, the code bender?
Yes.
Okay, Arduino
Yeah,
web editor.
Yes.
Does it seem like it's stuck?
Yeah, it does. I had this problem earlier too, I think. It just says
Okay.
busy kind of deal.
Yeah, and it keeps saying busy. Let's see here. I'll do that on my web editor. Okay, so import forward 3 seconds. Okay, for some reason it didn't want to import that, and I think it's because it's already there. So I'll try another one, forward 1 second, which should be nearby. Here is forward 1 second. All right, 1, 2. Okay, it should take about, for me, it took about 2 seconds. I would give it 20 seconds. And if it's still stuck uploading, you might refresh your editor and try again.
Okay.
So Felicia, did we have a Zoom meeting a while back to talk about robots?
We did.
You showed me how to make a battery really cook stuff.
Yeah, I did that for sure.
Yeah, that was a good test. Okay, let's see here.
I'm just going to close my web editor, restart it, and see if that helps out.
Okay,
But it won't be a big deal. You can continue to move forward.
all righty. How's everybody else doing? Have you got the forward for 3 seconds running? Okay, I got some thumbs up. All right, so let's see if I can show y'all. Here we are in Visualizer. Select camera. So this might be the part where I drop out using 2 cameras, but we're going to give it a try. Okay, so after uploading that, and I uploaded, or I don't remember if I have forward 3 seconds, or forward 1 second, but basically you can unplug it at this point or not, and then take it to wherever you're going to run the robot, and then set the switch to 2. And then to restart the sketch that's been loaded in there, press and release the reset button. There's that wheel twitch, and then there we go. I had to catch it from running off the table a couple times. Okay, let's, oopsie. Okay, next up then, I'm just going to talk a little bit. One thing you can try is changing your, they're called pulse parameters. In fact, before I talk about that, I'm going to talk a little bit about what those numbers really mean. So when you say servo left dot right microseconds and then 1550, 1450, or maybe servo left dot right microseconds 1700 and 1300, what's going on there is something that may be occurring to some of you. So I'll talk about that. So we talked about earlier about timing diagrams and how they could be used to turn lights on and off. Well, they can also be used to communicate instructions to a hobby servo. Now, the 1500 caused the, if you had a light circuit attached to P13, pin 13, you would see, and if you had measuring equipment, you'd be able to see that the light was turned on for 1.5 milliseconds. And during that time, what we did was we adjusted a part inside the servo called a potentiometer, so that in response to this signal, which repeated over and over again, every 20 thousandths of a second, that's 50 times a second. If you say 1/21 thousandths, well, the math takes you to 50 times every second. You know, it takes 50, 20 millisecond repetitions for a second to go by. And 1.5 milliseconds is the amount of time that the signal would stay high. And it would do that 50 times a second. And our servos were typically a little bit out of calibration coming out of the box. And so what we did was we used that screwdriver to adjust the potentiometer to set it so that this signal right here is exactly what would make the servo stay still. Now, if you send it a high time, which would turn a light on, or just basically briefly be at 5 volts for on the white wire of the servo. If you do that for 1.3 milliseconds, 50 times a second instead, what that's going to do is it's going to cause the servo to turn full speed clockwise. If you do it for 1.7 milliseconds, that's the 1700. This was the 1300 because the digital right microseconds, pardon me, is in microseconds or millions of a second, and 1300 millionths of a second is 1.3 thousandths of a second, or 1.3 milliseconds. Again, I'm rattling off stuff that the book introduces at a much slower rate because we're doing a 40 to 60 hour book in 4.5 hours. So I'm trying to give you the main points, and then, you know, going through the book on your own, either prior to teaching the class or at least keeping a couple of activities ahead of your students is going to be the way to make sure that you've got all this down. So 1300 is this with high times that are narrower or lasting less than the center signal, which makes it stay still. And then 1700 or 1.7 milliseconds is the on times or high times that makes the servo turn full speed counterclockwise. Students go through and they try out some different values. This is actually an excerpt from page 69, which is before we put the robot together. And so we try like 1520 and 1480. that's really only 20 millionths of a second above 1500 and 20 millionths of a second below 1500. So what you'd expect to see here would be the servo turning very slowly in the counterclockwise direction. And then here it would be turning slowly clockwise. 1540, well, that's a little further from 1500. So it's a little faster counterclockwise. 40 below 1500 would be a little faster. I'm sorry, faster counterclockwise. 40 below 1500 would be a little faster clockwise, and so on. And actually, there's also an activity in there where the students can measure how fast the wheel turns and graph it. And this is an example of the result of that activity where they're having where they're feeding different pulse widths, or what we call those brief high times, to the servo. And you can see that 0 RPM on the left here corresponds with 1500 microseconds. And when you're up to 50, you're kind of at half speed here. By 100 above, you're almost at full speed. We call that the linear speed control range, where if you give it a slightly wider pulse, you're going to get a slightly higher speed. Now, by the time you pass 1600, and we use 1700 just to keep the thing going as fast as it can possibly go. So, all right. So what if one of your servos is, when you use 1700 and 1300, what if one servo is turning a little faster than the other? Well, if you try to back off by 20 or 50, nothing's going to happen. So I usually tell teachers to tell their students that to make that first step from 1700, if you need to slow down the left servo, for example, to go from 1700 down to 1600 as a first step, and then either go a little up or a little down from there until they've slowed down the wheel that's faster. And that's another thing that's in the book. In fact, it's coming up soon here. Let's see here. Yeah, so this talks about the linear speed control and then the saturated full speed control. And let's see here. So again, that's right microseconds, and that's the number of microseconds to make that brief on time that the servo takes as instructions. And it takes care of repeating the 50 times a second for you. All you have to do is tell the servo how long to continue to receive, or tell the sketch how long those signals should continue before you do something else, like maybe a different speed, or in this case, servo detach will stop the servo signals entirely. And again, yeah, if your left wheel is too fast and it's causing the robot to veer to the right because it's going fast, well, you might want to move over, drop it by 100 first, and then decide whether you want to keep dropping it or maybe increase it a little bit, because it'll either start veering to the left or just less to the right, but still veering to the right. So that's how to slow down a faster wheel in order to get an exactly straight ahead travel. There's lots of lessons in here. Like this is, for example, a distance equals speed times time checkbox that would appear in physics and math. Apply it. And so what they do is they test, okay, well, if I run the robot for a second, how far does it go? Well, now I know that it goes a certain number of inches or centimeters per second. And what we can do with that is say, okay, well, let's say I want to go 90 inches. Well, I know that I'm already going 9 inches per second. So let's try going for 10 seconds to get that 90 inches. And so that's something that's in one of the activities for navigation. Let's see here. Then comes the computer science lessons that pertain to navigation. In this case, what we're doing is we're calling a function. So the function is down here, void example, and it's a couple of statements that are between curly braces. So this is something that the students are instructed to add to their sketch. And then if the function is called example here, then they can simply say example right there. And what that causes the sketch to do is to jump down to example, do the statements, and then return to the very next line in the main sketch. There's a special kind of, functions can be modified to accept values. So this is a function named pitch. And instead of having nothing in between the parentheses, it has int HZ, which is short for hertz. And what happens is if you say pitch and put 3500 in parentheses, not only does it go and find the pitch function, but it also passes that number into this variable that is being set aside to receive that number. Then what happens in here is it displays frequency equals, and then it displays the value stored in hertz, which is going to be 3500. And then it plays the tone, does a delay, and then jumps back and to the next line. Let's see. I don't see the name of that sketch. I kind of want to try it, but let's try this one instead. Okay, so here is an example of 4 navigation functions. So instead of using tones and displaying information about the tone in the terminal window, what we're going to do is have 4 different functions as kind of a starting point, as a way to ease into functions for students who might have never seen them before, especially.
Hey, Andy,
Yeah.
where do we introduce students writing their own functions?
Let me see. I should have opened the book right at the beginning of this.
Yeah, I'm trying to remember if and where we do that.
It is in chapter 4,
Okay.
and I want to say it's chapter 4, activity 6, 5 or 6, somewhere in there.
You have a much better.
Let's see here.
Yeah, custom functions is part of chapter 4.
Yeah, and so here's the book download.
If you recall the chapter summaries that are listed on the first page of the web tutorial, those summarize the skills that each chapter introduces.
So what was the page of that again for introducing functions? It was 119.
Yeah, I'm not looking at the page number, looking at the web tutorial, sorry.
Okay, no worries. 119. Boom. Oh, okay, I am on 119. So this is need to zoom on this a little bit. Here we go. Okay, so students start writing their own function call. Well, this is a discussion of how it works first. Okay, so simplify navigation with functions. So at this point, they've been just writing statements in line, one after another in their sketch. And this is where we start talking about, hey, you can use this function thingy. And so they actually enter it. So here's the sketch right here. They, ideally they'll have it side by side with their Arduino editor or web editor, Arduino IDE, whatever they're using, and they'll hand type it in. That's for definitely best results. So questions that occur along the way. Students who tend to load it and run it also tend to do poorly on quizzes and tests that might be asking about things like, what is a function? How would you call this function? Those kind of questions are in the back of the book, and it would also be fair game for quizzes and tests. Okay, back to the slides. So yes, I'm skipping a lot. I want to make sure you guys get the main stuff. There's also, so as far as main stuff goes, here's a forward function. It has a time variable that needs to be loaded. So here it says forward 2000. That's 2 seconds. And so when the sketch gets to forward 2000, it jumps over here, drops 2000 into the time variable, local variable. It's only temporarily active while this function is getting executed. And then what it does is it uses the magic statements for forward, that being 1700 and 1300, and then it delays for time. And so we get to study how using different times in different functions affect the robot. And so I would really like to do this program next. It's on page 123. This was a kind of a weakness in my setup, as I didn't leave the program name in there. Okay, so the program name is Movements with Simple Functions. It's in chapter 4, so I'd like everybody to try that next. Ooh, darn it. Movements with Simple Functions in the chapter 4 folder. Remember to put your 3-position switch in position 1 while you're loading it. Now for this one, if you want to, you can unplug your Arduino from the USB port and then set it on the ground. Then set the 3-position switch to position, or actually before you set it on the ground, set the switch to 2, then press and release the reset button, then set it on the ground, and it should do its forward, left, right, backward maneuvers. Okay, let's see if I can. Sorry, that's a little bright, I realize. Dial it back just a bit. There we go. Press and release reset. Oh, pardon me. I have it in 1. I needed to switch it to 2. So again, you want to hold the robot, switch it to 2, press and release reset, set it on the floor. Okay, so again, left, right, backwards. And then set the 3-position switch to 0 and go ahead and set it back on your table. Now would be the time to also reconnect the USB. Okay, how did that go? Thumbs. More thumbs, looking good. All right, good job, everyone. So the two things that I'm hoping that students get excited about here are, one, interacting with the sounds, especially students who might not otherwise be interested in robotics per se, are going to have some fun with experimenting with sound if they're interested in music. So we're trying to essentially appeal to as many different different interests as we can. Let's see here. Okay. With that said, next up is back to music. Okay, so you already heard the do, re, mi. We went from C7 to C8, I believe. No, we went from C6 to C7. And these are just the musical notes that you would see on the right side of a keyboard. And so this is an example so for earlier we introduced functions and then showed how you could use them with navigation. Here we're going to start with functions and how they interact with, or here we're going to start with arrays. And an array is a list of numbers. And there's some coding that's necessary to access each element in this list of numbers, these numbers being the notes from C6 to C7. And so this example program uses note of 3 to access 0, 1, 2, 3, the third element. So they try individual elements first. And then we go and do the whole thing, introducing a for loop, which is actually a reinforcement of something that was introduced in the initial coding lessons that were in your pre-workshop homework. So now we have this for loop, and instead of just printing the value of index going from 0 to 10, in this case, we're printing the value of the index. And for each value of index, well, note of index is going to go when first time through the loop, index will be 0. So note of 0 is 1047. So that's the note it's going to display in print statements and play. Second time through the loop, it'll be 1147, third time, 1319, and so on. So play notes with loop is the next chapter 4 script I would like you all to try.
Andy, can I ask a question about the code that you have up on the screen? If you could go back just one.
Can you see it now? Is it this guy? Okay, good.
Yeah, that's it. So right up at the top, you've got 2 lines that kind of describe that this is going to be about music.
Yes.
Okay. Do those 2 lines actually execute, or are they just labels?
Yeah, these were introduced as comments, although, that's a good point because I don't think I put that in your homework. Right after the functional stuff of, remembering, communicating, counting, and deciding, those being basic programming tasks. The very last activity, I believe, in chapter 1 talks about comments. And comments are either preceded, if it's a single line comment, everything to the right of a double / is going to be a comment, which means that it's ignored by the C compiler inside the Arduino IDE.
Okay, so its purpose is just to keep people clear about what's going on.
Yes.
But the execution starts at the INT line, right?
Yeah. Yeah. So this basically tells the Arduino, hey, this list of values is going to be stored in the note array. And this is the notation for take whatever, the thing inside the brackets is empty. So it essentially uses whatever it receives to determine how large the array is going to be.
Okay, so sometimes when you turn on your Arduino editor, it'll have information on that screen. Should you erase that and then just start all over again with what we're doing?
Well, generally what I do is I save my work and then I start a new file with the next activity's code project. Or in some cases, the next code project in the activity, if there's more than one. That way, students can go back and open up earlier programs and modify them. For example, this right here is actually the foundation for Whiskers navigation. And what will happen is just a little bit of code is going to be added right here to check the Whisker contacts. Let's see here. So it gets pretty tricky at the end of chapter 4. So we set up an array of speed values for the left and right wheels and an array of times, and then we go and say, hey, let's and there's a special maneuver function that they use. I'll talk about that in a little while. See, maybe I thought I was going to talk about that right in this neighborhood. I'm not sure why I'm not seeing it. Here, is this it? Yes, this is it. Okay, so this is a function that gets used a lot throughout the book. It's called the maneuver function, and it's something that the students write and test near the end of chapter 4. I think I'm not going to have everybody run it because we're running out of time to build Whisker circuits, but just basically maneuver 200, 200, and then what's it say? Is that 2000 or 3000? Can't see it because it's behind my camera. 2000. Okay, so 200, 200, 2000. That means that the left wheel will go full speed forward. The right wheel will go full speed forward, and it's going to do that for 2 seconds. Then negative 200, positive 200, 600 is going to make it turn in place for 1/6 of a second. And each one of these, like maneuver, well, that jumps down to the maneuver function. And then the maneuver function has set aside 3 variables. Well, speed left gets 200, speed right gets 200, and ms time for millisecond time gets 2000. And then it goes through and does all the work for you and jumps back up. And then you can call the maneuver function again with your next maneuver. This is a very cool, nice, simplified thing. And it's a function that students are going to find useful throughout the book. It's the same set of maneuvers. It's just an easier way to have it because this maneuver function, once written, can be copied and pasted from earlier sketches to later sketches. And then just use these function calls to send the program there and get the job done. Let's see. And did everybody get a chance to try the speaker tones? Sound good? Yep. There's a lot of musical opportunities there. I've even seen robotics groups where, one student in a contest would be responsible for the circuit, another for the main code, and then a third for the I'm starting the course code and I'm ending with a victory song code. All right, next up is Whiskers. Before that, I just want to take a moment to talk about another thing that I just wanted to make sure you guys were aware of. Wrong camera. Okay, here we are. That is that when you're assembling your robot, not only do you want to have the screwdriver that's in the kit, but there's this nice little wrench for holding the screws as you tighten them with the screwdriver. Another thing I want to mention is that when you're putting the battery pack in, these 2 little white nylon screws, it's very important when your students, if you have your students as opposed to a teacher's aide building the robot, it's very important to have those white screws as the ones holding the battery pack. There we go. So do you see that one of the white screws is right there and the other one is right there? Okay, so those are the white screws that hold the battery pack on. And the reason for that is because this little, this is what Felicia and I were talking about during the Zoom meeting that we mentioned the battery tests and heating them up. So this battery sleeve right here is really only a little thicker than cellophane. It's not very thick at all. And underneath it, you have metal surface that looks like what you see on the ends. Well, the problem is that that metal surface underneath the thin plastic here is also connected to the battery as a voltage source. So if you have a metal screw here, it might actually nick the battery as you put it in. And that might in turn connect the battery to the chassis, which is actually ground. And so you might have some battery voltage that's a lot higher than 0 volts short circuited to your battery chassis. So that's why it's very important. That's a very important APB. Another important one is simply that whenever you're done for the day with your shield bot, you got to remember to remove the barrel plug. Otherwise, your Arduino will continue to run and drain the batteries of power. Next up is whiskers. So these are the whiskers out in front of the robot so that the whisker gets pushed before the robot runs into something, or the whisker is the first thing to run into something and therefore gets pushed. And it gets pushed up against these electrical contact, one of these electrical contacts. This whisker gets pushed up against this electrical contact. This whisker gets pushed up against that electrical contact. And let's see here. Okay, we've got 15 minutes, cutting it close. So what I'd like us to do is I'd like you all to grab these parts. These are the whiskers, a couple of nylon washers, a couple of 7/8 inch, roughly 1 inch screws. I think these are 5/8 inch standoffs, so they're close to 1/2 inch. They're metal standoffs. These are called 3-pin headers. Then we want resistors with red, red, brown, and resistors with brown, black, orange. Looks kind of red in the picture, but it should really be brown, black, orange. This is on page 148 of your book. Okay, so gathering the whiskers, then gathering some 3-pin headers. Actually, since I see the screws and standoffs, I'll get those first. Okay, did you all get it done more quickly than I did, or are some of you still working on it? Thumbs up. You beat me, Catherine. Thank you, Bob. You beat me too. Let's see here. And I still see some folks looking around, so I'm going to give you another minute. Actually, I'll talk about the steps. So page 149 shows how to, you'll be basically unscrewing the 2 screws in the front of your robot by the breadboard, and then replacing them with these longer screws, washers. And it's important to hook one whisker around a screw above the washer and the other whisker around the screw below the washer as you put them together. And then this is what the circuit's going to look like. So page 150 has the circuit. And the important thing to remember about the circuit is that the red, brown resistors go to digital sockets 5 and 7. And then the brown, black, orange resistors, the 10 kilo ohm resistors. So these are red, brown is 220, and they go to sockets 5 and 7. And then the 10 kilo ohm resistors go between 5 volts and the 3-pin headers. The 3-pin headers are going to go in along with where the resistors are connected here on these rows on the right side of the breadboard. So basically, get the parts shown on page 148, connect the whiskers as shown on page 149, and then build the circuit as shown on page 150. And remember to leave your piezo speaker on the breadboard. Be very careful, because one circuit mistake will not likely to hurt any of the electronics, but the application has to be 100% correct. The circuit has to be correct. The code has to be correct. And your robot has to be calibrated, and etc. So I usually start the screws and kind of get them partway screwed in with the nylon washer and the put the nylon washer on the screw, then put the standoff on the screw, then get it started in that hole in one of the corner holes by the breadboard after removing the but don't tighten them down all the way. So then what you can do is take that whisker and kind of, I'll put the left one above the washer, and I'm just going to hook it in there so that it's hanging on to the shaft of the screw. Then I'll tighten it down. And then rinse and repeat, but for the right side, I'll go ahead and hook in the whisker below the nylon washer. Then tighten that one. I don't tighten them all the way first. I kind of just get them tight enough to hold the whisker, and then I turn the whisker roughly to where I want it to be. And then I tighten it. Now, when you've got the whiskers tightened down, you want them to be in front of the breadboard. not, their little flat areas should not be hanging over the breadboard. Like roughly a screwdriver's thickness in front of the breadboard, or basically like parallel to the front of the breadboard. Then we can go ahead and add in our 3-pin headers. So 6 down and 9 down. 1, 2, 3, 4. No, it's too far down. 6, 7, 6 down and 8 down from the top of the breadboard. Then connect the brown, black, orange to the between each 3-pin header and the 5-volt sockets. I feel like Bob Ross doing this. It's a good thing I'm not doing art though. Imagine little stick figures and smiley faces. And then the red, brown goes between each 3-pin header row and the P7 and P5 sockets. And I just dropped the resistor. So I'd like everybody to look up at the screen for just a minute. I just want to make sure that you all know that you want the whiskers to not be touching those 3-pin headers. So these are the 3-pin headers plugged into the breadboard. And it's only when you press the whisker toward the robot as though it's running into something that you want the whisker to touch the 3-pin header. Okay, that was it. Oh, thank you, Benjamin Smith, to everyone. He mentioned that when you have functions like setup or draw, that you cannot have 2 functions with the same name. You can only have function calls with the same name. So each function has to have an individual name. Your sketch can call it many times at different points within the sketch. Okay, so I have the circuit close up on the screen in case anybody finds that to be helpful. All right, can I get some thumbs up for everybody who's got it put together? Give me a thumbs down if you're still working on it. How about that? Anybody needs time, give me, okay, so thank you, Bob. Any more? Yeah, Andrew, good, good. Okay, so we still need, yes, Jessica.
Hi. So should we twist the whiskers together, wrap them around them together?
No. They should be, each one should be able to move independently because it might run into just the right side or the left side of something. And so we want them to be able to move independently so that maybe just the right whisker will bump into the 3-pin to its 3-pin header or vice versa, or both of them.
Okay, because the way that the picture looked, it just seemed like they were wrapped around each other, but okay, I will untwist it.
Oh, good.
I accidentally twisted them together, but okay.
They will cross each other, but not touch as they're crossing. One should bypass the other. There is a forward straight on shot that will show
There we go.
that. Yeah, if you could share that shot, Andy.
Can you see it now?
Yeah, I can see it. Yeah.
Yeah.
Okay. Thank you.
Oh, of course. Now, it is okay electrically if they touch each other. We just want to try to avoid getting them stuck against each other is all.
What will happen though, no, actually it won't unless they both touch the pins. So never mind. Catherine had a thumbs down briefly there, Catherine Woodruff.
Okay.
And now I see her adorable little dog again. How are you doing? Thumbs up or still thumbs down? Do you want to unmute and let us know what's going on?
Still working on it. I had a difficult time seeing the different colors of the lines on the parts that I needed.
Yes.
Yeah.
So for that, that was one of the reasons behind the find a magnifying glass in the homework thing. And then actually, I guess I qualify as an electronics professional, and at work, uh-oh, now I can't find my phone. Okay, well, at work, I use my phone because it has a magnifying feature. And so when I need to look at things that are really too small for my aging eyes, I go ahead and use the phone camera to zoom them up about 10x, and they look larger than life.
Andy, the jumper cables are not performing a function electronically on the circuit board, are they?
The jumper cables. So let me bring up the circuit again. So are we by jumper cables, do you mean like, for example, the one going between a breadboard socket and digital socket 4 here?
No, I mean the 3 pins that are connected together.
Okay. So what's happening here is that the whisker is connected to chassis ground. So the little plated holes that the screw goes through are eventually make their way electrically to the negative terminal of the battery pack and the ground terminal of the USB cable if it's connected. So this is a common ground, and it's considered to be 0 volts. And so because the whisker wire is connected to it, when I push on this whisker, this little part of that whisker is going to bump up against this 3-pin header. And what that will do, this 10K resistor here, I'm getting a little bit ahead of myself, but this lightly applies 5 volts to this row right here. And so the Arduino senses that 5 volts on P7. Now, when you push on the right whisker, this left, it bumps into this left 3-pin header. When it does that, instead of lightly being pulled up to 5 volts by this large resistor, this 10 kilo ohm resistor, it is hard shorted to ground, 0 volts, by the whisker, which again is connected to the ground because there's a plated hole on the BOE shield that makes its way to all the ground connections. So when the whisker touches this P7, instead of having 5 volts applied to it, it has 0 volts applied to it as a result of pushing the whisker. It touches here, and that changes the whole circuit, including what the Arduino senses.
Oh, thank you. Yeah, that.
You're
helps
very
a
welcome.
lot.
Now I had actually some nice little slides that were supposed to talk about that. So this is electrically the same thing. It's an excerpt from page 151.
Hey, Andy,
Yeah.
want to point out we are almost 5 minutes over.
Yep.
And I wanted to ask if you wanted to save the assessment material access for next time then.
Well, I'm going to send out an email saying, hey, everybody, you got to, make sure you can log into learn.parallax.com because that's where we'll be looking at the assessment material. Some teachers have had trouble finding it in their spam queue or in their inbox, or finding their old learn.parallax.com account that they did a long time ago. So just do your best. Not being signed up for learn.parallax.com by Friday it won't make us unable to do any of the activities, but it is a good thing that I'm going to assign for the homework. And then another thing I'm going to assign is just to basically, if you have to leave immediately, I'm hoping as many of us as possible will hang out at least till we get the robot running with the whiskers, get this troubleshot, and then I'll send you a set of instructions to build a new circuit that will, no, actually, yeah, I might send you instructions to do a new circuit, or I might just send you instructions to just make sure that your whisker robot is running just fine. And I think I'm leaning towards that. We'll see. It depends on how many people can stick with us. It should only take another 5 minutes to get our whiskers going. So as many of you as can, please keep hanging with me for just a little while longer. We'll get our whiskers running and test it out. So to test out the whiskers, you want to go to the chapter 5 folder and get display whisker states. Okay, so I'm going to open display whisker states from the chapter 5 folder. Display whisker states. Okay, and then when we run this, nothing will appear to happen, but after it successfully loads, then go ahead and open up the serial monitor. And it'll look like this with a bunch of zeros. Now here's where the fun starts, because when I push on the right whisker, nothing happens because I made some sort of mistake. I didn't have my 3-position switch in 1. Okay, so actually when your 3-position switch is in 1, which is important for this test, you want to see the a pair of 1s when the whiskers are not touching. Then when you press on the right whisker, you'll notice that the right digit changes from 1 to 0. And when you press on the left whisker, you'll notice that the left digit changes from 1 to 0. So my test currently is indicating that both my whiskers are functioning and I'm ready to move on. Your students may want to skip this test or ignore the fact that they're not getting the results that are explained in the checklist instructions from the book, but they absolutely have to have this working and tested before they can confidently move on to the next program, which is called Roaming with Whiskers, if I remember correctly. By the way, if anybody has to run because it's past it's past an hour and a half, we will have the YouTube video of this posted so you can catch up on that as well. So again, chapter 5, Roaming with Whiskers. And when you open up that one, go ahead and close your other sketch and make sure to close your serial terminal. And we can make sure that you're in position 1 or 0 when you load this into the Arduino. Okay, so mine is uploading and I heard the start tone and it says done uploading. So now the next thing to do is to take that shield bot, unplug the USB cable, plug in the battery pack if you're not plugged in. All right, we're still in position 1, so it's not moving. And I'm going to take it and set it on the floor. Okay, and then once you got all that ready, you can put the switch in position 2 and it's going to take off on you. And then you can basically use your hand to present the robot with obstacles by pushing the whisker up against the, whoa, got away from me. By pushing the whisker up against the 3-pin header. Stephanie, was that fairly visible? I wasn't able to look at the screen while doing it.
Yep, I see your hands. Yep. It's a little overexposed, but it shows the action.
Okay, good. So that is the test to see that the Roaming with Whiskers sketch is working. And I think what I'm going to do is I think I want everybody to just make sure that their Roaming with Whiskers sketch is working. And you can also change the times in the functions that make the robot turn in order to tune the maneuvers a little bit. So
Andy, can you copy and paste that code in the chat?
Yes.
You have a request for it.
Okay, so it'll take me a second because what I have to do is the chat only takes so many characters. So I
Oh,
need
that's
to,
why.
yeah, so I need to delete as
Why
much
don't-
as,
Why don't I copy and paste the tutorial webpage where it is so it can be pulled off of there?
okay.
instead? Yeah. Okay, so the roaming with whiskers can be copied and pasted off this tutorial page.
Oh, yes, we're going to learn.parallax.com for
I
that.
already have it.
Okay.
So I'll just paste that link right there. So we're good. No need for you to do that.
All righty.
Andy, this is a question.
Okay.
You have a special folder in which a lot of the code is inside the folder and it's organized and it's labeled. Is there a YouTube video that you guys have that talks about that process, how to find it? See what's happening with me is I have to run a PC and a Mac at the same time.
Mm-hmm. Mm-hmm.
So all of my work with Arduino is on the PC and everything's calibrated, everything works. But what I have to do is after your lesson is all over, then I have to go back and kind of type everything in over there and test everything. But the
Okay.
good news is everything is working.
Oh, excellent.
I just have a two-step process and I'm slower than everyone else. You know, because of my, I don't have the ability to cut, copy, and paste to go between a Mac and a PC.
Yeah. Yeah. Okay.
Yeah. So other than that, the lessons are working, everything's working great. It's just slower for me.
Yeah. So, well, the process of downloading and unzipping your folder and then accessing the various elements is going to be documented at the beginning of this video. So when I send it out, I'll try to remember to also mention the time at which we went through the demo for that during the earlier part of this clip, because that's the best one I know of. I don't know that that's anywhere else on a YouTube
Okay,
video.
Yeah, that would be perfect. Yeah.
Okay, great.
The link is in the chat again.
All right, so how many of you have got your whiskers running? Got some thumbs up? Okay, so I would say that to use the, because I went ahead and did the whole demo of running the test code. And if your test code doesn't go exactly like mine did, it usually means that there's a circuit mistake somewhere and you can go hunting for it and find it. And after finding it and correcting it, it should pass the test. And then you'll be able to roam with whiskers correctly. So what I would like to do is just for homework, make sure that everybody's whiskers is running. And then if you already got your whiskers running, maybe tune it a little bit so that you like the distance of which it turns. Now, there are other activities in the book, and what we're going to do at the start of the next workshop session is infrared. I was thinking of having you guys build it, but I think we'll all just build it together at the very beginning of the next workshop session. So I'm leaving that for then. So light homework, it's just going to be, here, I'll show you quickly. Let's see here. Where is the homework? Okay, yes. Okay, so for homework, we want to have you watch a curriculum tour video. I'm going to skip the infrared detection. We're just going to do that together as a group next time. And then just make sure that your whiskers are running nicely and try having it roam around and if you have cats, kind of supervise because they'll want to show the robot who's boss. or at least our cats do. And so we'll talk about infrared and light following and all that stuff next time. So before we stop recording, are there any more
Yes, I have
questions?
a question.
All righty.
Hi, Andy. So we were wondering, does the orientation of which, like the resistors, the way that they're inserted
Such a
into the
good
board,
question.
is that like, does that, I don't know if we have, yeah, it's giving us 0 zeros when we press down on the whiskers.
Okay, now
So
how
I'm
about,
wondering
so
if-
is 0 0 when you press the whisker? Is it 1 1 when you don't press the whiskers?
Yeah, yeah.
Okay, so you're perfect. Now, but that is really a great question. And I have an answer. I'm just looking for the right slide.
Thank you.
Of course. All right. So the first part of the answer is this resistor here is not a directional device. Whether you push current through it this direction or this direction, relative to the stripes, it doesn't matter. It resists the flow of current in either direction. However, the light emitting diode, if we were to have built a light circuit, which the students will do much earlier on, this is a directional device. So if you happen to have this plugged in backwards, a diode is actually like a one-way valve. So if you think of a resistor as a constriction in the hose that slows down the flow of water or electrons, you can think of this as a one-way valve, where if you put it in at the end of the hose and you connect it backwards, nothing will come out. If you connect it forwards, it'll go ahead and spray water out. But in this case, it'll either light up when current is flowing through it, or if you have it in backwards, it will prevent the current from flowing through it. So this is an example of a polar device, a device with a positive and negative terminal. And then the resistor is just a simple, I don't know that non-polar is ever really used for resistors, but yeah, it's direction agnostic. It does not care which direction the current flows. It's going to slow it down in either direction. And if you think about AC current, like when it goes back and forth, yeah, it'll just go back and forth through a resistor as well. Okay, any other questions? So again, we're going to have you watch a video. We're going to have you sign up for, or make sure you can log into the learn.parallax.com site and just basically polish your whiskers application. And feel free to get with me. I can meet with you over Zoom briefly to do any troubleshooting if you feel stuck. And with that, thanks for coming, everyone. You're welcome to stay after and talk about all kinds of stuff. But we are going to go ahead and stop the recording now. Stephanie, if you would do the honors.
Absolutely.
So Andy, I got a quick question on a general question.
Okay.
Can you hear me?
Yeah, and Stephanie, let's leave it on here. Yes,
Oh.
Mark.
I don't think you need to record this. I'm just I've done some programming with other languages, but I notice here when you use an if or a for or a while, there's not an end statement. Is that correct?
Okay. Yeah, that is correct. The way it works is, let me see, I'll open up that's a very good question. Let me open up
I mean, this roaming with whiskers has an else if statement.
Yes.
And I've noticed in the for statement, how does the program know when it's ended?
Let me get to, yeah, so roaming with whiskers, I just need to get it opened up here. Okay. I think it's probably better to just do it in the IDE file. Open. Roaming with whiskers, I had it open already, didn't I? Yep. Here it is. Okay, so your question is, we have if, and then some statements. So what defines what's contained by the if? Now in PBasic, for the basic stamp, it would be contained at the bottom end by an end if. Now in Arduino, which is a C++, is basically a little wrapper around the C++ programming language. In C language and C++, the way it works, do you see how when in the IDE, when I click this upper curly brace, that the lower curly brace has a little square that appears around it?
Okay, okay.
What that is showing you is that these two curly braces are containing what to do if this if statement, where both the whiskers are 0, turns out to be true.
Right, okay.
And then if it's not true, it's going to continue if we have a chain of if, else
Okay.
if, else if,
Okay.
else. So let's say that's not true. Well, then it'll go and check and say, hey, is just the left one 0? Well, if that's the case, we'll call the backward function and then the turn right function and make it back up for a second and then turn right for 0.4 seconds. And I'd recommend making that 0.7 seconds. I think that's a better turn.
Okay.
And that's what I'm talking about tuning your whiskers, is you want to make the turn go whatever distance is going to be most favorable. And so turning for 0.7 seconds, I think will get you turned so that if it's a real obstacle that's just sitting there and it's not your hand that you're going to take out of the way, it'll definitely back up and then make a turn to go in a new direction. And so, yeah. And so each of these, when I click the opening curly brace, and often you'll see it look like this. Most coders put the opening brace here and then the closing brace down there.
Okay. Okay.
I just couldn't bring myself to do that for beginners, so
That's okay.
I did it like that.
And then you have a closing brace way right before void. Is that
Okay, so
closing
when
the
I
whole-
click
yep.
that and then come up, you see which one is,
Ah. Oh, it's way above there.
yeah, so this last curly brace is basically the loop, the built-in Arduino loop function right here,
Right.
starts with a curly brace, and then everything between its opening curly brace and this closing curly brace is what gets executed over and over again automatically by the
Sure.
Arduino. So all that right there from, oh, sorry.
Would you say the else is just the last thing that ends the whole if statement, the plain else?
Yeah, so this else is definitely this closing brace right here for the catch-all condition of else, which just makes it go forward a little bit before
Sure.
checking again.
So if,
But that's closing the else.
Well,
yeah, but does if always need an else?
if does not, you could just have this if, and then it would only, respond when you pressed and held both whiskers against
Right.
the posts. And then it's talked about in the earlier programming tutorial, which again, in 4.5 hours, I can't get it all
Yeah,
presented.
that's where I
Or your
noticed
heads
it
would be
was going through
swimming.
those.
But yeah, so for example, I could actually say, I could do it like this. The only difference is that it's no longer mutually exclusive. And then
Right.
I actually don't know what to do with the else off the top of my head. I'd have to think about that a little bit.
Okay.
You could actually, so your catch-all condition, if it was just if statements, would be to go forward if none of them are true by a 50th of a second before automatically repeating the loop function and starting all over again. So this for our practical purposes is as good. It still works, but this was a point in the textbook where I wanted to introduce the else if and the idea of the code having a mutually exclusive, it's only going to do this,
Sure.
and then bail out down here. Or if this isn't true, it'll check this. If this turns out to be true, it'll only do this part and then bail out down here and repeat the loop. So that's why I decided to put that here. We're about halfway into the book, so that the students will have had some coding practice by this point.
Yeah. Okay, thanks.
Yeah, my pleasure. Any other questions before we go ahead and shut off the recording? Okay, so Stephanie, go ahead, and thanks for coming, everybody. You're welcome to stay. I'm glad to talk with you about all kinds of stuff, be it classroom or more questions if they occur to you.